No. Yeah. So with that, let me sort of begin my talk. And there are quite a few bits to this here, but let me say upfront that I won't be covering everything because it's late in the day. I'll just tell the simpler part of the story, and people who are interested, we can discuss later. So as we've sort of seen in the few turbulence talks that we've had in this meeting and before, is that people always talk about either irreversibility, chaoticity, or the intermittent nature of turbulence. And, uh, and this has been known for a while, and especially in the Eulerian framework, people have been looking at it for years. Uh, then something sort of new came up, a recent approach which dealt particularly with this issue of irreversibility, and this had to do with certain Lagrangian measurements which were made a few years ago. So what's the Lagrangian measurement that people made, and the references are here. So, the first work was by Haitao and others, an experimental work, and then Rahul's group followed it up. Then Priyanka, who's sitting there, also looked at some aspects of this in rotating flows. But just to sort of tell you what the measurement was done by these chaps here was the following. So they tracked fluid particles in fully developed turbulent flows, and this is one such trajectory. The color, as it moves along, the color denotes the amount of power in this trajectory. So essentially, you measure the total kinetic energy along this particle, and when it's sort of red, it means that the particle has sped up, and when it's green, it means it has slowed down. So from there, they sort of extracted for any given trajectory the total the time trace of the kinetic energy as a function of time. And when you zoom in various regions, what you find is that so this is all in stationary state. So the mean energy is, of course, constant. But what you find is that particles in any given time window sort of gain energy slowly, and then they lose energy rather rapidly, and then they again start gaining energy slowly. And so this was sort of dubbed for reasons. So basically, they sort of claim that this is particles taking off, flying, and energy crashes suddenly, and then you again slowly build up energy because the system is in stationary equilibrium. And from there, what these people essentially, so I'll basically spend more time explaining the question than what we've done. What they essentially did was to calculate a sort of energy difference across a time scale. So you take kinetic energy here and a little further apart in time tau, you measure the difference, and you want to look at the distribution of this chap on various values of tau. Essentially, you want to pick out the asymmetry in this gain in energy and loss in energy as the particles move. And from there, you can play other standard games like you would do with a thermostat, essentially try to see if certain sort of fluctuation relations hold or not. So the question which we started to explore a little was, all right, that's about the irreversibility, but it's been sort of drummed into our head, especially is the fact that turbulence is also intermittent. Typically, we've been told not to care too much about the chaotic nature of the flow, but just the intermittent and irreversible nature of the flow. So the question that we wanted to look at was this Lagrangian irreversibility, how is it connected with the extreme statistics of Eulerian dissipation rates? Essentially, if you take a fluid and you measure the energy dissipation rate at every point in that fluid, and you draw contours, then you have, so epsilon bar is the mean dissipation rate. Then you have regions in yellow which are 4 times the mean rate. In purple, it's 6 times the mean rate. So you have these extremely localized regions where there is an anomalously high amount of dissipation locally happening. Of course, this is dynamically evolving. It's a snapshot. So the question that we wanted to ask is, are these energy crashes in any way correlated with these extreme small-scale dissipative structures that are there in the flow, and this sort of fluid particle sort of samples this as we go along? So of course, I should point out that this sort of question was asked and answered by Jason Picardo, who was a postdoc with us. He's now a faculty member at IIT Bombay, and Akshay Bhatnagar, who's a postdoctoral fellow at Nordita. And for details, this is the archive preprint. All right. So what's the strategy? The strategy is the following. We sort of have 3-dimensional, fully developed turbulent flows. I'm not going to tell you exactly how one gets it, but by solving the Navier-Stokes equation in suitable ways. And then we seed the flow with traces, so they will act like fluid particles. And then we are going to track the trajectories of these particles. And then we measure kinetic energy along these particles, as was done in the experiment, as a function of time, from where we can calculate a power, which would be the rate of change of this kinetic energy. And eventually, what we would like to, as a definition of what irreversibility would be in this language, is the asymmetry between the positive and negative tails of this power distribution, right? If the rate of gain and the rate of loss was exactly symmetric, then the negative and the positive tails would be coincident. And at the end of this talk, you'll see that as a quantitative number, one looks at the ratio of the cubic moments with a negative sign because of the skewness and say, okay, that's a measure of irreversibility. This number being large, more irreversible, number small, less irreversible. All right, so here are the power statistics. So now the question that we wanted to address was, is there a causal connection between irreversibility and these extreme structures in the flow? So the way to do it, and here I will spend most of my time, essentially, is as we follow the trajectory and calculate this power along the trajectory, we keep track of where the particle is in the flow. And so while we make the statistics on P, we are also conditioning it on whether the particle is in an extremely, in a part of the flow where the statistics are extreme, namely there's a lot of dissipation happening, or whether they're in sort of calmer regions. And so in blue, we show the plot for when you don't condition the statistics, and the other two are when you condition the statistics. So there are two lines for each color, which is essentially the negative tail we reflect just to compare the asymmetry. So the first thing we sort of notice is if we only consider portions of the trajectory when the particle is zipping through regions of extreme dissipation, then the curve is opposite to what you see in blue. As, the PDF. It's the PDF of the power. I've reflected the tails. So what you essentially see is if you only condition the statistics when the particle is going through these strongly intermittent structures, then the rate of energy gain is actually more than the rate of energy loss. This is completely different from the measurements that Hightower and others made, which we recover, of course, when we look at the full statistics. If you look at regions where the flow is rather calm, so it's only when the dissipation is less than the mean, then you see the asymmetry goes in the other direction. So the naive expectation, which was born out of all these studies of Hightower and also, Rahul, Akshay, and Dhruva's paper, was that particles probably should lose energy faster when they're in regions of rapid dissipation. This is certainly wrong, as far as we could tell. So this naive expectation is wrong, and what we find is that extreme dissipation actually leads to regions where there are takeoff events. I mean, this is a happy thought, given most of us will be taking a flight soon, going back to our parents. It's better than flight crashes, right? So what we now wanted to understand was, where was this coming from? So for that, and I'll go easy on the algebra, but all I can say is that one can, from the Navier-Stokes equation, actually derive an equation for the power, and one can show that it depends on epsilon, the dissipation rate, and the other factors. Now, skipping some of the steps, what one can again show, and this is not averaged. So what one can show is in regions of intense dissipation locally, because these structures are localized, this equation is actually, one can drop these terms, and then you can see that this is approximately equal to just minus epsilon and u dot grad p. So the question is, if this picture is correct, then this chap must be preferentially large and negative. And do we see this? So there's an argument, and I won't have time to go through this, but what you can show is in high Reynolds number flows, where inertial effects are subdominant, you can show that the viscous forces balance the pressure gradients only in regions of intense dissipation. So let me go to the evidence, because I just have a minute, and the evidence is the following. So what we do is we plot the PDF of u dot grad p, again, same style. The negative tails have been reflected, and you see the same behavior. So if you look at the entire flow, so you don't care where the particle was going, and you measure u dot grad p, then you find, this is actually negative u dot grad p that we've plotted. Okay, it's there. So what you then find is both the tails are coincident, and that's something that people in turbulence knew for a long time. But if you actually look at condition statistics, then you find that this chap is indeed much larger, the right tail, the positive tail, because I've absorbed the minus sign here, is indeed much larger when you're in a region of extreme values of epsilon. So this, I didn't go to through the theoretical derivation, but just the numerical proof of this. This sort of, I'm nearly done. This sort of suggests or substantiates the argument that we make that when a fluid particle goes through a region where there's extreme Eulerian dissipation, the velocity vector of this fluid particle anti-aligns perfectly with the gradient of pressure. And if I have time, I'll just explain that mechanically. And then you can look at the cosine of this angle and you actually sort of substantiate it a bit more. So this is the sort of final plot because this was the results that people had before. So if you measure this sort of single measurement of the irreversibility, ignore these points because I'm not going to talk about that at all. You find that it's irreversible if you consider the full statistics. If you condition it on mild regions, the level of irreversibility actually increases. If you condition on statistics where it only goes through intense structure, the sign changes as well. So this is it, essentially. The epilogue, I will not go through how we substantiated this a little more. So the conclusions are that regions of intense dissipation are not places where tracers undergo rapid energy loss. This is the counterintuitive sort of claim that we, or well, hopefully we are right, that we make. Actually, there are pressure-driven takeoffs which happen in such intense dissipation regions. And essentially, the sort of party line is flight crashes occur not because of the intermittent nature of Eulerian fields, but despite it. Because wherever there are these structures, there is a pressure-driven takeoff mechanism, which is completely contrary to what people expected with the first experiments. Okay, I'll end here. Thank you.